Ladies and gentlemen, welcome to the Roundtable, Still Not Dead, Developments in ICE. This session is sponsored by AVL. Your moderator is Lindsay Brooke of SAE International. You are invited to submit questions for today's Roundtable through the SAE International's WCX app. Ladies and gentlemen, Lindsay Brooke.
Quite a few familiar faces in the audience.
Yeah, sure. Okay.
Still waiting for Fabian?
Yeah.
Fabian, I think he's on his way.
Good morning, everybody. Still waiting for one panelist.
Wait. Okay. Here he is.
Well, good morning, everyone, and welcome to the evolution of the internal combustion engine, as we called it last year, still not dead. And despite the many predictions for the ICE, which is over 120 years old now, we still see it going strong. And I drove down to this Congress in an electric car, which was great. But it made me think, driving this car, of one technology that is seemingly humble, yet extremely high tech, and has everything to do with what we're talking about today with internal combustion engines, and that is the piston. And this piston seems to be, I was off of my desk, I think it's a contemporary piston, and you can see the technology in this has been evolving for over 100 years. This is either a casting or a forging in aluminum. It has to withstand incredibly high temperatures and pressures. Its topography on the piston crown is extremely dynamic geometry to deal with the air-fuel charge with a direct injected engine. As you can see, its skirts are extremely short, only extending down a little bit below the wrist pin center line. It's got high-tech anti-scuff material built into the skirts. And a lot of people would say, oh, pistons, this is old hat. These things consume an enormous amount of finite element analysis time and CAE time, and they continue to evolve, and the piston of 10 years from now will likely be different than this piston. So this is a long evolutionary path, and the humble piston isn't really so humble, and we make hundreds of millions of pistons every year right now for the current market. And where the market is going is probably still going to be in the many, many millions of pistons for engines. You know, even the most conservative forecasts about where the electrification tipping point is still say that the ICE is going to be predominant for quite a long time, probably through the middle of this century. As the previous panel, how many folks were in the previous panel? So you heard a good panel that talked about some of the things. We'll have a little overlapping conversation, but some of the things like electrification, when that tipping point is going to be, and what is going to happen to ICEs, and they're going to evolve, and they're going to evolve with hybridization, and a lot of them will be specifically designed to work in hybrid applications. One of our panelists in our preliminary discussions had told me that the ICE will have room to coexist with EVs. And I believe that. As sales of battery electrics start to take off, who knows when they'll really take off in volume, but the ICE is still going to be there. The industry is transitioning into an eventual electric future. Again, when is that going to be? But in the meantime, hybrid powertrains are going to continue to blossom. Different solutions are going to be coming out, and that's really showing that the ICE isn't dead after 120 years. What are the industry's opportunities to increase efficiencies in the ICE and thus significantly reduce CO2? What technologies are expected to extend the life of the ICE while meeting the customer expectations that the previous panelists talk about? We still have to make vehicles drivable, efficient, pleasing, high performance, etc., and meet regulatory standards. So that's why we're here today, and we've got a fantastic panel. I can't be more excited about the panel we've got here today. In alphabetical order, we've got Scott Bailey, who's CEO and president of Tula Technologies, and each of these experts is going to have a chance to discuss their company, what its status is in terms of technology development, what the latest and greatest is. But Scott's right here. Peter Davies is Senior Director of Powertrain for Garrett Motion, major turbo system supplier. Thank you. Dr. Uwe Grebe is Executive VP of Global Business Development for AVL. Uwe's there in the middle. Masahiro Moro. Moro-san is President and CEO of Mazda Motor of America, Incorporated, and I think you just recently added the CEO title to your position, so congratulations for that. And last but not least, Dr. Atsushi Taraji. Taraji-san is Deputy General Manager at Nissan Motor Company. And Nissan, of course, playing in a number of fields, being an EV pioneer and also really pushing combustion engine technology forward as well. So, as before, we'll be taking questions from the audience, and please send them to me, and I think a couple of them have arrived up here already. But I'd like to start out with Uwe. AVL, of course, is an engineering services company, do business across the globe with automakers, suppliers, other agencies. AVL knows what's going on, and so I wanted to ask Uwe to kick this off by really giving us his global view of the major regions and maybe the future prospects for internal combustion engines going forward in those regions. And also tell us, Uwe, about the regulatory environment a little bit in the major regions.
Yeah, well, Lindsay, thanks a lot, and probably let me start out with this statement. I believe the ICE is not dead and will be around for quite a long time, because we also need it to fulfill the transportation of the masses, to really move people and move goods. But if you like, I can take you on a tour around the globe and try to talk a little bit about what we as AVL see. So here in North America, you're very familiar with this market. We have significant move into electrification, and I think that is a good thing. But I believe in the long run it will also be balanced, because there is requirement for long distance travel, for hauling goods, and so there is, from my perspective, a significant future for the ICE. When we go to Europe, Europe is currently, from a regulatory perspective, well, probably at the forefront, making it extremely difficult to comply on the CO2 part. There are more stringent regulations that are announced and that are in place, asking for significant reduction of the fleet, and there's also mandates for what is called CLEV, or the zero level emission vehicles, that is vehicles in essence with a plug. We see in Europe a lot of development into the electrification, but also a huge future for what I call an electrified ICE. Hybrid technology really enables the internal combustion engine to improve further on efficiency, and I think with the clear targets also on the criteria emissions, and in Europe it is very close to everybody what the air quality situation is, talks about banning diesel with older emission standards from cities, but what we see as AVL is there is technology there that you can take the IC engine out of the discussion about air quality and put it on the solution side for that. So a huge push into electrification, but also here I think the electrified ICE will have a huge future. Let me just touch on two regions. What is very interesting is India. India is pushing electrification a lot. There is the FAME program that that supports electrification, but also there, I mean, the task is to move a lot of people on an affordable level, and that is where the internal combustion engine comes into play. And let me close on China. I think looking into China is probably telling a lot, because there is new energy vehicles, again vehicles with a plug that are mandated, but that is the region where we see a lot of interest in new architectures for internal combustion engines, where there's work ongoing, where there's interest on how can we move the thermodynamics further, what are combined processes, what is the electrified IC going. So let me probably wrap up here. I think on a global perspective, electrification and also plug-in electric vehicles, they are increasing a lot, and I think that is a good thing. There's a lot of places where that is the right solution, but again, I come back to my ingoing statement, the internal combustion engine is not dead, and we have regulatory environments that are challenging, but we have the solutions.
Mm-hmm. Very good. And Scott Bailey, the last time we had talked, you had just returned from China, or you were going over to China with Tula Technologies, and I'm wondering what OEMs and the people you're talking to in China, what they're saying on the ground about the future of ICE versus, say, hybridization versus electrification.
Well, I think, Lindsay, Uwe hit it right. There's a big push, clearly, for the new energy vehicles. But there's also a growing recognition that, and as the new energy vehicle credits start phasing out, the reality is that there's an absolute requirement to take the internal combustion engines and keep moving them to the next level. So new concepts, new architectures, at Tula, our technologies, dynamic skip fire, that looks interesting because it does pair very well with electrification. 48 volt mild hybrids with dynamic skip fire creates additional synergies. So those types of solutions are attracting quite a bit of interest for both gasoline applications and then relatively recently on the diesel side as well. And it's, I think no matter where you are in the industry, there's an understanding that, okay, we are on a march towards an electrified future, but that march absolutely has to include clean, efficient, ideally low cost, and maybe perhaps a little bit less complex internal combustion engines, simply because now we have to start combining technologies to really get the maximum environmental benefit. And I almost want to reject the title of the panel, because I don't think it almost sets up electrification as somehow the opponent of internal combustion engines.
Right.
And I think
rather complementary.
Rather what we really need to think about is, on this path towards an electrified future, and to build on your point, there's going to be roughly 2 billion more internal combustion engines produced between now and 2040, 2045. I think it's an obligation to make them as clean and as efficient as we can, and it's not really an either or, it's how do we have the best net environmental benefit and still enable the transportation everyone needs.
So the Piston guys shouldn't start worrying yet, is that what you're saying?
Not yet.
Yeah. And Teijin-san, you know, Nissan, interesting perspective, you know, pioneer in EVs with the Leaf, and also doing some very interesting work in new combustion engine strategies too. Could you give the audience some insight into what it's like to work at Nissan? Is there two different camps, or like Scott said, is everyone kind of working together to combine what the EV and electrification guys are learning and developing and what the combustion engine guys are?
Yeah, good question. So as you know, the Nissan push the pure EV now. So how to continue to develop the ICE? It's very important in Nissan.
Yeah.
So to talk about these topics, I would like to introduce current the concept of powertrain strategy. Matching with today's topic is still not ICE. So current powertrain situation is very similar to the dinosaur story.
Dinosaurs.
Of course, ICE is dinosaur, mammoth is pure EV. So now, you cannot see the dinosaur anymore in this world. Then, ICE is also the same destiny or not? If not, how to survive of this world continuously? Then, I think importance is a three key points from the dinosaur story. First is downsizing. Second is homothermic. Third is the wing. Then electrification is one of the solution of wing.
The wing meaning aerodynamics.
Yeah. How to reduce weight and cost? That means downsizing. The third is homothermic, then also covered by electric. So, what is the most good solution for the electrified powertrain in Nissan? Of course, now we push in the battery. Then we found out the solution of series hybrid, so-called e-power in Nissan. Then we can concentrate it to improve the thermal efficiency and EV component like battery and motor. The solution of series hybrid is only the combination of artificial ICE and the out of state of EV component. Then currently we push the series hybrid as well with ICE and EV. That's our scenario to push the electrified powertrain. That we can use same component, both of ICE from EV. Continuously, we want to expand the data solution among three units without investment increasing. That's our scenario.
And so you're seeing internally the teams are starting to work together and,
yes, exactly now.
and think for each other, that kind of thing anymore. Yes.
Of course, several years ago, the team is separated.
Oh yeah.
The direction is different.
Yeah.
After the e-power solution, currently our team become together on the same direction. It's series hybrid also for Nissan is a good solution for the future.
Very interesting, and again proves the electrification plus ICE equation there. You brought up some points that I wanted to ask Moro-san as kind of the car guy on the panel here. And as CEO, he gets to drive vehicles that are in kind of late prototype stage before they're introduced to the consumer. And I'm wondering about the definition of a great engine today. And Moro-san, you know, when you get in a vehicle, how do you feel, whether it's your seat of the pants or the aural characteristics of the engine, or just how it feels, you know, just holistically in the vehicle? You know, how do you consider a great engine today? And is that definition going to change? A great engine today in 2019, will what we'll call a great engine in 2025 be different?
Well, I think it's interesting questions. We really love the engine sound, vibration, even smell, the feeling of life. That's been for a long time, and we want to keep that going forward. So the feeling we get out of the engine, together with the chassis, suspension, transmission, I think we just able to kind of feeling of extending our body and arms that connect to the road through the car. That feeling is, I believe, very exciting. Mazda see internal combustion engine a centerpiece of technology of the car itself. Today, we are inventing SKYACTIV technology to improve the thermal efficiency. And we see a much opportunity to further push the boundary to improve thermal efficiency to the ultimate limit. And that is Mazda's focus. And we have a very sound and robust so-called building block plan to eventually couple with electrification technology to transit towards sustainable future. But I think why Mazda put focus on the internal combustion engine to be more efficient is because electrification devices can be smaller. By using best out of internal combustion engine, the battery size smaller, and we are thinking about the total CO2 generation from wheel to wheel.
That's interesting.
So I think generating electricity requires CO2, discharged.
Right.
So how we can minimize as a whole? We believe internal combustion engine play a big role going forward. So in future, so internal combustion engine will be much efficient, yet provide that feeling of life. So that is how Mazda see internal combustion engine.
Very interesting. And just to follow up, Mazda has, for years, was directly associated with the Rotary, and we'll talk about Rotaries in a little bit. Pioneered Miller cycle engines, was an early turbo adopter on the Rotaries. Do you see vehicles in the future kind of being identified by the type of engine, and this is a question for everyone, the type of engine that's in them? I mean, it wasn't long ago we'd have DOHC on the side of a car, or rotary engine, that kind of thing. Is the industry moving past that kind of direct identification of type of engine with the vehicle, or are there still going to be customers that still are looking for something kind of like Hemi? I mean, Hemi's a great example, but there are other examples too.
Well, I think certainly different engine can provide a different feeling.
Yeah.
But a feeling that customer can feel, not us pushing this is SKYACTIV or this is a rotary engine. Customers see the value out of how they feel. I think an internal combustion engine has a different characteristic. I think this is one of the beauty to provide a choice for the customer. We continue develop our internal combustion engine to provide a stress-free, more linear feeling together with the other vehicle components, so that customer really think this is my loved horse. Okay. So even creating bond between car and driver.
Gotcha. Very good. I'd like to take this opportunity for the panelists to kind of give everyone an update on the status of where their companies are right now, where their development is. We have 2 OEMs on stage, and we have other suppliers and technology companies. And I thought this would be a good place to just give them a platform to give us an update. And Fabian is with Acades Power, and I encourage you with Acades and with Nissan to go, in particular, to go online, and also Tula, go online and see the videos of these technologies. All the companies have great visuals that show how these work. I kind of wish we had them on the big screen here, but Acades is pushing opposed piston two-stroke engines that are kind of fuel agnostic. Is that a fair way to explain the Acades engine? And I know you had some programs with Aramco, ARPA-E. If you could, Fabian, if you could just give the audience an update on where Acades is right now.
Yeah, absolutely. Thank you very much, Lindsay, for giving us the opportunity to be part of this panel. Thank you to the other panelists. It's a great honor. So Acades Power was founded 15 years ago with the idea of modernizing the opposed piston engine and leveraging all the latest and greatest technologies that have been developed over the centuries to improve the internal combustion engine and make it what it is today. So what we've been able to do over these past 15 years is really solve some of the fundamental challenges of the opposed piston engine to really make it a platform that we can use to demonstrate the capabilities in terms of emissions and efficiency. The opposed piston engine is an engine that by itself, by architecture, has lower heat rejection, and that provides a lot of flexibility to manipulate the engine calibration, the engine design, to really optimize it and improve emissions and fuel economy. So one of the projects that we had the chance to do that we're still working on, that was funded by ARPA-E, it's the development of a gasoline opposed piston compression ignition engine. So this is a project we have done in partnership with Argonne National Lab and Delphi Technologies, with the help of Aramco Services as well, to demonstrate what the potential is for a light-duty pickup truck opposed piston engine. And actually recently, earlier this January, we actually drove the vehicle, and it's impressive to see that the opposed piston engine certainly has a different characteristic, different feel, but feels like an engine. It was in a truck, fits in the truck, and it moves around just like a typical vehicle. This is a vehicle that we previewed at the last year's auto show as well, in partnership with Aramco. Another very exciting development that we are starting to see now in our labs is a program that has been funded by CARB. And CARB has been funding us to develop a heavy-duty opposed piston engine running on diesel with the target of reducing greenhouse gas emissions by 15% compared to today's standards, at the same time as reducing NOx by 90%. So showing the potential that with the right technology, you can really reduce fuel consumption and emission at the same time. And I think what's interesting in thinking about that and looking at electrification as well, we also see that electrification will enable very efficient IC technology to really make it to the marketplace. There was an example in the previous panel about, for example, electrically heated catalysts, right? So if you have electrically heated catalysts and the energy available on the vehicle, then maybe you don't have to worry about that. Maybe that enables, and takes the equation that we have been struggling with, like diesel emissions and these type of things out of the story, out of the discussion. So there's really a lot of synergies that can be seen. Another project that we are also starting in partnership with Nissan, actually funded by ARPA-E, it's the ability with electrification to actually simplify the architecture of the engine. So our engine has 2 pistons, 2 crankshafts per cylinder, and the ability of electrification is to take away the gear train that connects those 2 crankshafts and actually put an electric motor on each one of them to provide full control of the volume of the cylinder, and also eliminate the gear train, the noise, the weight, the cost associated with that, make the engine more efficient, more integrated in electrical machines. So this is another way where you can see there's really a synergy, certainly a coexistence, but even more a synergy. And I think as also John Haywood mentioned in the previous panel, when you look at the life cycle analysis of battery electric vehicles versus current production internal combustion engines, there is a benefit for EVs today, but once you start optimizing the internal combustion engine with electrification, there is a significant opportunity to reduce the life cycle impact of these powertrains without necessarily having to shift all the way to EV. So we see a great opportunity, and certainly appreciate the support from the industry and our suppliers and partners in advancing this technology. We want to provide and help our customers find the best solution to meet the environmental needs as well as our customer needs. Like in the previous panel, really emphasized the fact that you need to make sure that whatever you produce is going to be what the customer wants, appreciates, and feel. So.
Now, the Acadi's engine, you use a supercharger as kind of, as I recall, kind of an EGR pump. Is that correct for that engine?
Right, so the opposed piston engine does not do any pumping by itself.
Right.
So currently we couple it with a turbocharger, which actually does most of the pumping work, and obviously high efficiency turbochargers. You know, we're working with Peter Davis and several programs as well, you know, with Garrett technologies, which is the heart of the pumping system of the opposed piston engine. The supercharger is there just to provide a slightly additional pumping benefit to balance out the pressures. So
Okay.
it's a more complex air system, but again, the engine itself does not do any pumping. We don't need the engine to pump.
Okay, and we've got some other turbo advocates with Nissan, you know, has done various boosting strategies. Mazda's got boosting engines, and that's queuing me up for Peter Davies from Garrett to talk about boosting, turbocharging technology, where it's going, and what opportunities you see kind of going forward with extending the ICE's life, Peter.
Okay, so thank you, Lindsay, for the introduction. And first of all, maybe I'll just touch on the name Garrett. It's an honor for me to be working for Garrett again after 25 years. I was actually hired by Garrett. We were known by different names in the meantime, but it's great to come full circle. We're serving a global industry on all fuels and in all segments. So I need to touch on commercial vehicle, I need to touch on light vehicle, diesel, gas, CNG, alternative fuels during the course of the discussion. Probably a lot of it's going to be talking about gasoline, light vehicle, but I need to talk about the technology that's coming into those other areas as well. Over the next few years, we're really going to see a step change. I think to some of the earlier comments, this opportunity of collaboration between the internal combustion engine and the electrification side of the vehicle, it opens up a huge wealth of opportunities for us to optimize the internal combustion engine in new ways, to go after specific parameters instead of spreading ourselves very thinly across a very wide range. So right now, a modern gasoline engine, you can see a best BSFC point of 225 grams per kilowatt hour. This is with a millicycle. What the turbocharger is doing here is not being the best boosting device. It's being the enabler for advanced combustion. It's providing the boundary conditions and ultimately the oxygen to provide the oxidant for the fuel. So our job has shifted from just make it a little bit better to consider it at the system level and find out how do we get to millicombustion at 225 grams, ultra millicombustion at 200 grams. These are incredible numbers for a gasoline engine. Maybe even to lean combustion down into the 190s and 180s. So if we're successful in providing the right boost conditions, boundary conditions for this type of combustion, then a vehicle becomes 5% more fuel economic, maybe even more than that. And with the combination of that and the electrification, which is coming, recuperation of the braking energy, etc., then we really do have a path to reaching the targets that have been set to us by the European Union of minus 30% based on a 2020 norm by 2030. And in that sense, I think we have real hope that the internal combustion engine is certainly not dead before 2030.
It's interesting. It's interesting.
Yeah. So we have plenty of scope. If I can touch on just two technologies maybe, long before we get to electrified boosting, we're all going to see a massive wave of variable geometry turbines coming into gasoline. With Lambda 1 requirements, wide range, high performance, etc. Variable geometry is here already in a few applications. By 2025, it's probably going to be approaching 40%, maybe even 50% of the world's gasoline engines in volume sales. So that's the first thing that's going to happen. Second thing that's going to happen is electrification. There's electric compressors. My own company's involved in electric compressors for internal combustion engines, for fuel cells as well. There's plenty of other competitors out there in the electric compressor space, and they're all providing lag-free performance from a turbo engine. The next step after that is electric turbo. Electric turbo provides all of the functionality of an electric compressor, but it does it in one package, and it provides other things such as energy recuperation, which an electric compressor cannot do. So as we find our way to coexist with the electrified powertrain, as the vehicles settle down as to what size the battery is, where are the e-machines in the vehicle, then we can optimize the boosting system to give you really transparent performance and no compromise on fuel economy.
And will we need, say, a minimum 48 volt architecture for driving some of this?
I think essentially 48 volt is the minimum. It's by no means the highest level. My own company now has plans for series launches on both 48 volt and high voltage applications with e-turbochargers.
And Moro-san and Teijin-san, are we likely to see more boosted production engines from Mazda and from Nissan? Turbocharged?
Well, from Mazda point of view, I think very efficient combustion allow us to couple with a more boosting function. In fact, we are introducing a turbocharged engine to our Mazda 6 and 6.5 and increasing the range. That is downsizing in a way, but the modern technology allows us to smartly boost up the torque and the power. If customer is looking for that, then we deliver that.
Yeah.
But if I speak about diesel engine, that could be a slightly different.
Yeah.
I think a bigger displacement will be essential to reduce our overall emission levels.
Okay.
So we explore a lot of different way to make our internal combustion engine more efficient.
Okay. Teijin-san?
Yeah, thank you. We recognize that the turbocharging system is one of the key items for the future because we consider the turbocharger is one of the what can I say? That is exhaust recovery, one of the exhaust recovery systems. So even series hybrid, again e-power in Nissan. We need to say e-power.
That's your brand name for it. Yeah, yeah.
E-power also important component is turbocharging systems to improve the maximum thermal efficiency point. Again, because it's one of exhaust energy recovery systems.
Yeah.
So totally to say the turbocharging system is a very, very key, and we hope from the OEM side, then please make it much more cheaper.
Oh, right. So from boosting to cylinder control, infinitely variable cylinder control on a digital control basis. Scott, what's happening with Tula?
Well, thanks, Lindsay. Bit of background. Tula Technologies, a 10-year-old tech company headquartered in Silicon Valley. We're one of the odd companies there that works on powertrain stuff. But we are a controls company. We're not a hardware producer. And what we've developed we call dynamic skip fire, or DSF for short. And what DSF is all about, and in many respects it's the ultimate extension of cylinder deactivation, because we need an engine to be capable of having each cylinder controlled independently. And we overlay on that a control scheme that in many respects is a pulse density strategy. So if the torque demand for an engine is very high, we fire every cylinder, every opportunity. And by the way, we do make that decision each time a cylinder is coming up to be fired. So it's an event by event control strategy. So if the torque is high, we just fire every cylinder as an engine normally would. If the torque demand is very low, we might fire 0 cylinders. And then we've got varying firing frequencies in between, depending on the torque demand of the from the vehicle, from the driver. The key to making, there's 2 keys to making this a reasonable approach. One is when we do fire a cylinder, we try and fire it as close to its optimal thermal efficiency as we can. And then we do so in a way that there's no objectionable vibration. So that comes to managing very carefully and algorithmically the selection of which cylinders fire and which are skipped and so on. At the end, the whole point though is to improve fuel consumption, and our first production project or program was introduced a year ago with General Motors. So on their large 5.3 and 6.2 liter V8s, GM, the trade name for them is Dynamic Fuel Management, but that is, underpinning that is toolless DSF. Now on a larger V8, we might see a 13, even a 15% improvement in fuel consumption. 4-cylinder engine, maybe roughly half that amount. But the whole point of doing this is to get more efficiency out of the internal combustion engine, and in particularly at lower loads, because almost independent of the drive cycle, we like to focus on peak brake thermal efficiency, which is good. We have to keep driving that up, but where we're going to do the most, I'll say, environmental benefit is making sure that at lower loads that the engines can be as efficient as they possibly can. So our philosophy is one of really creating the I'll call it a software-controlled variable displacement engine that dynamically downsizes the engine depending on load and tries to make it as efficient as it can be all of the time. But one more thing that I think is important, and it ties in a bit to what Mauro-san was saying, that no technology can cause a sacrifice in performance.
Right, I wanted to ask everyone about that.
Because
go ahead.
For example, and I'll speak to mine, but there are other technologies that have the same impact. The consumer, the driver, wants the maximum torque that engine's going to produce, and they want it right now when they need it.
Right.
And I think that's especially important when consumers have the opportunity to drive pure electric vehicles too. You're going to get addicted to instant seamless torque. But you have to be able to produce an efficient engine that's pleasurable to drive, that doesn't cause any compromises for the driver. And I think, as we talk about technologies, and Peter mentioned, no lag-free turbo and so on, those are other parts of this whole equation, I think, that are quite important.
And cylinder deactivation, Uwe, Fabian, the OEMs, cylinder deactivation seems like something where you can reduce pumping loss, you can reduce a lot of things and really improve the engine. Is this something, well, for Mercedes, is this viable for Mercedes? Is this something that Nissan and Mazda would be looking at? And Uwe, you see the whole kind of technology landscape.
Yeah.
Where is the world going in terms of cylinder deactivation? And your companies, please chime in here.
Maybe let me start on that. I mean, in the past, cylinder deactivation, and it got introduced on V8s here in the US years ago. General Motors was out there with this active fuel management.
But didn't Mercedes V12 have it first?
Mercedes had it on a V12, but I think we focused on the fuel economy in the past with the pumping losses. What I think is extremely important, you can do a load management, and thereby you can do a temperature management, you can do an exhaust gas temperature management. So it enables us to control not only the efficiency of the combustion engine, but also the temperature control of the after treatment system. So it adds another level of flexibility, and I think it is one element that needs to be considered when we think about the internal combustion engines of the future.
Very interesting. Is this something that's interesting to Nissan? Is cutting out a few cylinders?
Yeah, in case of Nissan, we have a strategy of a transmission. We have a CVT transmission, so engine operation load is very high.
Right.
than other the manual transmission and the DCT system. Then the value of a CDA became lower. But for the future, we explore the new value from the CDA. So currently we have the discussion about the CDA with not only for the conventional ICE, but also the e-power. And we also want to consider the emission value from CDA.
And you call it CDA would be a cylinder deactivation system.
Yeah. So CDA can use one of the cylinders. One cylinder size is become bigger. By using a load become higher for one cylinder. Then entropy become higher than by using all of cylinder. That's a value we currently explore under discussion internally, but unfortunately, currently we did not achieve that good solution by the CDA due to considering CVT technology strategy.
Okay, very good. Some of the questions have come in, quite a few of them, and one question that I got from everyone the last 2 days, knowing that Moro-san from Mazda was going to be on the stage and also Uwe was going to be on the stage, was really what is the future of the rotary engine? And we saw it as kind of a nameplate for Mazda. I mean, really it was the single interloper, let's say, in combustion engines over the last 100 years. I mean, it was all piston engines and all of a sudden the Mazda rotary. And it was really the only competitor that kind of broke through the piston engines and has been associated with Mazda. And I know AVL as well worked on some rotary range extenders. Moro-san, kind of tell the audience where rotary development stands at Mazda.
It's a lovely question for us. The rotary engine is so at heartland of Mazda's engineers. And we never forget, never give up. We continue developing that. The rotary engine is very, very unique compared to normal piston engine. Rotary consume many things, different things.
Yeah.
So fuel, hydrogen, everything.
It's multi-fuel.
Multi-fuel. And compact, high power, maybe suitable for sports car, or hydrogen, ultimate environmental friendly capability. So we have a wide range of potential for rotary engine, and one of the usage that would be effective is as a range extender concept, which is a very, very nice fit because compact and quiet, no vibration, and at constant RPM, fuel efficiency pretty good.
And is that constant, because I know AVL worked on this, Uwe, is running a rotary in a very narrow kind of operating range, is that the solution to some of the emission issues that the engine had years ago?
Oh yeah, I mean, Mazda showed that you can handle the emission in a wider range. It helps a lot, of course, when you restrict the engine running, let me say, a load curve or a sweep through the engine speed. And I can only second what was said. I mean, with the basic architecture of the rotary, the central shaft, it matches very well with an electric motor. And one thing that we see is when you talk about battery electric vehicle, the big product cost lever is the battery. And by the way, also the battery has a lot of implication when it comes to the CO2, the greenhouse gas that is associated with producing the battery. So it makes sense to balance architectures in a way that you design battery for a certain driving range and use range extenders. And here the rotary is one of the possibilities where you can nicely fit a pure electric architecture with a flat battery panel with a range extender that does not harm you on cargo space, on passenger cabin space.
And would the range extender be naturally aspirated, or would it need to be boosted?
Well, I think it was mentioned before, when you boost it, you have another package optimization. And I
Right.
think it is not only a question of the efficiency that we get, it is a question of what is your, let me call it package or vehicle package efficiency of the internal combustion engine. I think that is something where we probably also need to change our thinking in a way of what is my minimum box volume of a range extender that I can bring in there if I talk about such a BEV extended or an EREV architecture.
Very good, very good. A lot of questions coming through. One of them that's kind of related to that, will the ICE be smaller than 2 cylinders?
Yeah.
I mean, will we start to see, as maybe a range extender piston engine, single cylinder?
So yeah, it's very interesting. Obviously, in order to preserve the efficiency of the engine itself, we want to make the biggest cylinders possible. When it's time to generate only 30, 50 kilowatts or less than that even for a range extender, then we need to downsize the engine. When you downsize the engine, you downsize the cylinders and the pistons, which reduce its efficiency. I think a single cylinder by itself has also a lot of challenges in terms of balance. So one of the things that we're actually looking at with the opposed piston engine is the fact that it naturally balances itself. With 2 pistons in the same cylinder, we're able to have a fully balanced engine. And with crankshafts rotating in the opposite directions, you can have no moments at all. So you can really have an engine that is as well balanced as a rotary engine and still have the very high efficiency potential of a single cylinder with very low heat losses and area to volume ratio.
Very good. I'd like to change the topic to fuels, which comes up in all of these combustion engine discussions, and it made me, seeing the VC engine, variable compression ratio is kind of the ideal to be able to use different compression ratios, different fuels, really kind of get around the knock issue. Maybe Teijin-san, you can talk about future fuels, and I'd like Uwe and Fabian as well to talk about what you've heard about fuels coming. We've talked about higher octane fuels, maybe a 95 standard in North America that would be similar to that in Europe. But you guys have done a lot with this VC engine in terms of optimizing that.
Yeah, thank you. That's a question. So VCR has a potential to apply the all-over fuel without any improvement of hardware by the software. And the future, by the combustion sensing, it's without any calibration. That's the future story, but in the future, by the sensing the combustion and the knocking and the combustion stability, without any calibration, we apply to the all-over fuel by the VC turbo. That's a point is the e-Power also has the opportunity to apply all-over fuel because in case of e-Power, the transient performance is almost nothing. Almost use only the same position. So that sometimes the fuel issue is under the transient.
The fuel issue is under the transient.
Yeah, so the e-Power also easy to apply the all type of fuel in the future. That's all. We always consider how to continue to use the same technology in the future.
Yeah.
Yeah, that's
Anyone else
thank you.
like to comment about fuels? I mean, this is a big issue.
Yeah. Well, I would like to comment on the fuels. I think when it comes to the octane number, I think that there is potential, and it was discussed before in multiple panels over the years. I think there is an opportunity for efficiency to leverage and to get it to a higher number. But I would like to change a little bit the topic on power to X. and on synthetic fuels, because we have a lot of discussions on what is the right utilization of what are renewables, and I mean with photovoltaic and with wind energy we get into green electrons, but I believe we cannot only think of using them in battery electric vehicles. I think going through synthetic fuels, that is what we need to promote, because it takes the internal combustion engine out of the equation of CO2. As soon as we do carbon capture, take it out of flue gas, or even use biomass to get to the carbon. But I think we need to start intensely on fuels that are based on renewable energy, because that, for me, is what we need to get solved for the internal combustion engine. We have a wonderful propulsion system that takes us on a long tank range, and you can so easily top the tank up. It is about making fuels available that tap into the renewables. That for me is one of the biggest topics that we need to all together promote and work on a global basis.
Very good. And I mentioned your engine being kind of fuel agnostic.
Right. So I mean, I think more generally, I think along the line of what Uwe is saying, I think what's important is to really consider the total equation. This is the life cycle of carbon emissions. So when you optimize the engine in conjunction with the fuel, then you need to find a solution that ultimately has the highest efficiency and uses a fuel that has the lowest CO2 footprint. So one of the challenges I think that I see actually happening in industry is SI engines, by definition, don't have the same efficiency potential as compression ignition engines. So if SI engine is what is used today, but requires a fuel that needs a higher octane to really extract higher efficiency, but that fuel actually has a higher CO2 footprint, then is that really the right equation for the whole equation, looking at the full life cycle analysis? So I think these are some of the things we need to take in consideration as well. When you think about the long term, what is the fuel, and because the fuel infrastructure obviously is a very significant investment for the community, what is the best solution ultimately to achieve the lower CO2 emissions globally? Very
interesting. Speaking of fuels too, I've been asked too about Mazda diesel program. Could you give us a status report on that? And you guys have done a lot. You had a racing program, looked at diesel. Can we still look forward to diesel from Mazda? Is that not dead yet?
Absolutely. We never give up, as I said. And we are working on regulatory office, and we want to make sure 100% transparency, so that we provide capability to meet with the stringent regulations without any funny technology.
Funny.
I think this is very important statement for government and for us in terms of credibility. And we are very happy to see the progress. So I think that diesel technology, I believe, is still one of the solutions going forward. Right now, it's a little bit climate is tough for diesel. But technology-wise, I think diesel and gasoline come together in the future. To be ideal combustion engine. That's how Mazda see it. So that's why we continue to invent that side as well.
Well, we're approaching the last 10 minutes here, and I wanted to run through just some technology trends and kind of survey the panelists on kind of hands up or hands down on whether they think these technologies will be common in the next 5 or 10 years. So everybody can show their hands. Number one, further downsizing of engine displacements.
I'll go with that.
We'll do it via software.
Okay, there you go. Cylinder deactivation. Again, 5 to 10 years. Engine downspeeding. Dana? Energy recovery systems and more precise management of exhaust temperatures.
Two ends.
Yeah. Absolutely.
Adoption of Miller and Atkinson cycle operations.
Yep.
Variable compression ratio. Wow. Gasoline particulate filters.
Yeah.
Interesting.
Yeah.
Very interesting. Wow. And on the structural side, non-metallic engine structures, composite blocks, these kind of things. Wow. Interesting. Wow. Have you guys looked into at Acadi's kind of non-metallic? The Acadi's engine's unbelievable because it started out as kind of aero engines that were really long, and now it's just the size of kind of a suitcase. Lightweight as well. So, and you had mentioned kind of going to motor control versus a geared crank arrangement. Any prospects for going non-metallic with that engine?
So
architecture?
there are certainly some things that that can be considered. I mean, just like non-metallic components are being developed for four-stroke engines, they can also be developed for the opposed piston engine. I think right now we're at a stage where we are transitioning into lighter weight materials. As our technology matures, we're adding more complexity, more attributes. So now weight is another one that we have to, to design for and innovate on to make really the opposed piston engine fully, compatible with the existing vehicle requirements.
And last question too, any outlying technologies that could just fly in from Mars that would be complete game changers in this regard? We've seen Scotch yoke engines, we've seen sleeve valve engines. I mean, there's been any alternatives, but really in the last 100 years, only Mazda's development of the Rotary has really kind of broken the piston engine hegemony.
Yeah. Well, let me just throw one thing in, and that is further improvement of the combustion system. When you look into the race engines that are out there today that use pre-chambers and what you can do with that, when you take a look at what large gas engines did in the past, we see here another step that we can take on the thermal efficiency of engines and on the control of engines, on the control of how dilute you can go with the combustion. So we are not at an end. We are at a point where there is another introduction of technology, and it's not necessarily that as something that has a price tag on it that is absolutely hindering you from taking that next step.
And again, we had mentioned the kind of coming together of diesel and gas technology, of diesel compression ratios coming down, gas compression ratios going up. What are we thinking, to your point, Uwe, about compression ratio over the next decade? Continue to go up? Well, and of course, it can be varied too.
I think it is about going on a variable displacement. There are solutions out there. There's great work that Nissan already did in getting something in the market. Yeah. And there are a lot of solutions out there. What we are working on is to make that as easy to implement in an existing architecture as possible, with a telescoping connecting rod that is running, that is working, and we are also working on industrializing that together with EVIS as a partner. So I think it is moving up. Of course, you reach a threshold where your thermodynamics gets into conflict with the mechanical efficiency on that. But being variable adds another lever of optimization to the engine.
Well, you can see that. I mean, I've seen your connecting rod, the prototype for it. It's a very sophisticated thing, and of course, the Nissan VC, the kinematics are unbelievable. You really have to see this video because there's a lot going on in the lower end of that engine, and it's certainly optimizing the combustion system, but also optimizing NVH and so forth in these solutions. You add one thing and you take away another, right? There's no free lunch in any of this.
So, Lindsay, I had something else to add around the downsizing theme. I don't necessarily see downsizing as just simply reducing the size of the engine. I see it more as as the vehicle park grows in size, in the size of the actual vehicles, it's how do I use this engine platform that I have in larger and larger vehicles.
Yeah.
And this is an aspect where lag-free boosting, so electrified boosting, can really turn an engine which is not capable of powering a larger vehicle into something which is very capable. And the operating points that we're asking the engine to work at in the future, with the increased degree of hybridization that will be there, will allow us really to optimize those engines in totally different ways. So I'm still on the side that there will be future downsizing, but in the sense of using engines in larger and larger platforms. And we see it in China. We have natural barriers in China for tax brakes at 1.5 litre, for other tax brakes at 2 litre.
Yeah.
And you know, you can't just go to 1.6 litre and still sell a powertrain in China. You have to keep raising the bar on those smaller engines.
So we won't be seeing a 500cc cylinder deactivated, highly boosted Mazda Miata anytime soon.
Well, I think our SKYACTIV technology right now, we increased the compression rate of gasoline engine from 11 to 14.
11 to 14, that's a big jump.
And we brought compression rate of SKYACTIV-D, diesel engine, from 18 to 14. SKYACTIV X right now is a 15 to 16.
And that's your SPCCI, yes.
And going forward, I see higher compression is better. That's our view.
Interesting.
And that is a breakthrough again to bring a high efficiency for the combustion going forward. So we are working on that.
And I'm glad you brought that up, because the previous panel talked about HCCCI or some sort of lean burn, maybe spark-enabled solution. What's the latest on your program?
Well, I think right now SKYACTIV X we call SPCCI, which we are controlling the combustion through a fireballs, which is an interesting concept, so that we maximize combustion charged area, so that we can get a best efficiency out of that system. And we are start introducing that from the region where more CO2 requirement is stringent, and deploy one by one for other regions as well.
Okay.
So we are looking forward to hit the market, maybe Europe first.
Okay. But it's in production for Europe now, is that clear? Is that
we are going to be in production soon.
Okay. Last 3 minutes, and this is the pain question of adding this technology isn't necessarily technology that people will go into the showroom and buy some of these internal systems, some of these enabling systems. So cost and complexity become issues. And I wanted to just get from the panel, how do you deal with that when you're innovating a technology? You know, Scott, nobody goes in and says, I want the DSF, but I know it gives me more fuel economy.
Yeah, it's really an extremely important point, and independent of the technology.
Yeah.
And we've talked about a lot of things. A couple of things show up. Every new approach that brings in new degrees of freedom allows you to do more optimization, but as you take that approach, now you've made the calibration task for the OEM significantly more challenging.
Tougher.
So part of what I think we have is a requirement on all of us, no matter what basis we're coming from a tech standpoint, is how do you make the OEM's job easier? How do you provide machine learning tools for calibration, things like that, that will allow them to get from where they are to the next generation? Because I mean, every OEM that I've interfacing with is trying to sort out what powertrain technologies, the conversion to electrification, the adoption of autonomous drive, the conversion of sedans to crossovers and SUVs, and there's such a challenge for the whole industry to sort out how are we going to do all these things, which technologies, and then you get into cost, because the consumer at the end of the day probably doesn't care as long as we do a good enough job in terms of drivability. So the part of what we have to do is not only provide the technology, but we have to provide the tools. And whatever we can do with less complexity, with less cost, obviously is going to favor some technologies over others. And who the winners will be is still TBD, but
very interesting. Anyone else want to weigh in on cost? Moro-san, you know, your job is to sell cars in North America, but they've got to be compliant cars, and they've got to have good performance, good efficiency, et cetera. And it's kind of like safety technology. Some of this stuff you can sell, and some of it you can't sell on the showroom floor.
Well, I think we put customer at the center of everything we do.
Sure.
That's the most important point.
Yeah.
Of course, we have to comply with any kind of regulation, safety regulation, environmental regulation. That's a norm. But always customer feel good as they drive our car. Otherwise, our products end up with a commodity. We refuse to be a commodity. So that's why we are investing and put the energy to find out a smart way to provide performance and environmental capability at the same time.
Very good. I have one more question for Taejin. We just hit the 000 mark, but I've got to ask you, you know, VC was a real big leap for Nissan, putting that system into production. Was there internal resistance on cost? You know, looking at the benefits of the engine and maybe as a technology statement versus, there must have been guys at Nissan saying, well, this looks pretty expensive.
Yeah, good question. So by now, one innovation needed one value, but from now, one innovation needed several value. So VCT value is not only the compression ratio. The VCT value is NVH reduction. Then we can remove the balancer.
Right.
And multi-link system of VCT is good to the long stroke. That generally by using a long stroke, the engine height become larger. But by using multi-link system, so engine can be the compact. So currently our engine is not so long stroke, but by using a multi-link systems, we have an opportunity to improve the engine height. And the long stroke cause heat loss reduction, and flame propagation distance becomes short, then lean conversion also easy to good.
So there's benefits to all of
we
this,
have a lot of,
Classic.
we give a lot of benefit to the VCT. It's very important. Even if we have only one solution, we cannot develop the VCT now.
Interesting.
Yeah, everybody believes that a lot of value in Nissan.
But we could talk for a lot more time here. I've got more questions. Some questions came in. One of the questions was, are the OEMs still doing R&D work on engines? And clearly they are still doing that. As the panelists have said, even though suppliers are key in this. I want to thank our panelists today from Acades Power, Tula Technologies, AVL, Garrett, Mazda, and Nissan. Thanks so much. And clearly these things are going to be around for a long time. So thank you for your attendance.